going to share our project on carbon footprint comparison of AI models on different platforms. This project was done for CSC 407, and it focuses on issue that is becoming more and more important in computing sustainability. And I'm Farjoz, and my teammates are Momana Khatun Jinia, Shaida Begum, and I'd like to thank our faculty for this guideline for a 9-week research guidance. Let me start with the introduction of our project. AI models such as BARD, MobileNet, and EfficientNet are now widely used in student project, but this project demand a lot of computing power, which increases carbon dioxide emission. This is especially critical in a country like Bangladesh, where electricity is mostly generated from fossil fuel. Even small project can add to the carbon footprint. What makes our project novel is that it is a first cross environment study on student level training in Bangladesh. We standardized dataset and hyperparameters for fairness, highlighted the difference between light and heavy models, and tested the reliability of CodeCarbon against SmartPlug readings, which showed agreement within about 20%. In the now, why does this matter? In Bangladesh, fossil heavy grid running the same AI workload produces far more carbon dioxide than the renewable rich countries. Students here increasingly rely on pretrained model, yet they have no clear guidance on whether cloud or local setup are greener. At the same time, universities are under pressure to reduce their carbon footprint. They need real evidence to design lab policies and teaching practice. But most exciting studies emphasizes large-scale data center, while student-scale computing has been ignored. Our work contributed in 4 ways. One is sustainability, the second is policy, and the third is research, but last and not the least is awareness. Next, let me connect our study with related work. In Doge study, they actually research on the carbon intensity of AI across cloud instance. They showed the emission strongly depend on whether the energy resources are renewable or not. And the Boaja reviewed a framework for estimation carbon emission. They stressed the importance of including regional carbon intensity. But again, there is no validation in the classroom scale. And the next slide, that race 2 is the Verdencia study. They actually talk about the AI practice and found that monitoring and benchmarking can reduce energy. And Lu and Liua and studied Chinese industry and showed that AI can sometimes rise and sometimes reduce emission depending on the context. But both slides were studies were micro level, not focused on small scale model training. That this left a second gap: no empirical measurement of carbon dioxide at this student level. Well, in the next slide, from this gap, we formed 3 research questions. And the main research question was which environment, cloud or local, produces lower carbon dioxide emission for student level pretrained model in Bangladesh. From this main question, we have 2 sub questions, which is RQ1 is about what are the measured energy used in carbon dioxide emission of a scaled model in each environment. The second RQ was is how accurate is CodeCarbon compared with SmartPlug reading. Our study addresses this gap directly. Well, from the main RQ, we train 12 model in both Kaggle versus Kaggle and VS Code under the same hyperparameters, so providing the first student scale comparison in Bangladesh fossil heavy grid. The RQ1 was we identified a clear split lightweight model like ShuffleNet and MobileNet were greener and local desktop, while heavy CNN and such as BGG19 and DesNet produces far lower emission while run on cloud GPUs. The RQ2 was we validated CodeCarbon against SmartPlug reading. The agreement was within 20%, providing the CodeCarbon is accurate enough for a student. The unique contribution of our work is not only shows workload specific guidance, heavy model to cloud, lightweight to local, but also validate CodeCarbon as a reliable tool for student level research. And the next slide, I will let me explain how we mapped this RQ's experiment. From the main question, we compared carbon emission from training all 12 models in both Kaggle and VS Code, measuring total energy emission. And RQ1 was we looked at detailed energy and emission patterns for each model. And RQ2 is we measured local lengths with both CodeCarbon and SmartPlug. And the next slide actually shows us the 12 model that we trained for our research, six for vision and six for NLP. The dataset is VCG text classification, jackfruit, and jackfruit leaf disease images. The environment, as we said, the environment was Kaggle and VS Code. And this is also a parameter that we used in our paper, which is for validation is SmartPlug and repetition for the model for their validation. Output collected and analysis tool validation matrix is actually discussed in this, what discussed in the paper. And now I'd like to call my next presenter for continue this presentation.
Thank you, Fatih,
Moving
for
to
giving
Engineer.
me the flow. Now let me. Now you're seeing the workflow of our project. Uh, now briefly walk you through our methodology. We begin by scoping the problem, comparing cloud versus local training at the student level, focusing on Bangladesh Fusofer guide. Before running anything, we fixed our results question and evaluate metrics so result could be consistent. Next, we prepared our students protocol, same code base, same needs, CDS, same dataset. So both environment were fire. Our two setups were Kaggle GPU for cloud and a local desktop with PS Code. Next slide, we are seeing that we run the experiments. Each model was tracked twice in both environment with results saved in CSV logs. Energy and emission were tracked using CodeCarbon, applying Dhaka carbon factor and validated locally with SmartPlug for real work socket reading. In this analysis stage, we compare carbon dioxide energy training time, accuracy and efficiency defined as accuracy per carbon dioxide. This structured workflow made our study repetitive and fair. This is the matrix equation we have used in our to show our results. Findings. Cloud crowns emitted 21.9 lakes of carbon dioxide than local. The total was 0.444 kg on cloud base, 0.56 kg locally. Cloud also used less energy and was about 3 to 4 times faster. Studies show that their difference was significant, but they tend to favor cloud, especially for heavy models. Likely modified light supplement, modeling, and distilled bud were greener on locally with up to 80 to 90% lower carbon dioxide. Heavy CNS like BGC, Desnet, and efficiency were much greener on cloud with 60 to 80% lower carbon dioxide. So the choices of environment really depends on the model type. To check accuracy, we compare with smart plugs. The error was mostly 20% around, which is acceptable. For example, supplement was 6%, while design once it showed minus 20% overall. The test providing carbon convert relevant for student resources. Efficiency, we calculated efficiency. Both setups are close. Cloud and had easy on heavy models, with local was faster for lightweight ones. Cloud is faster and greener than for heavy models, while local is better for lightweight ones, and looks like CodeCarbon can sustain for reaches as long as bulleted is done. Now I'd like to call Shahida for his part.
Thank you, Genia, for giving me the opportunity. So let's start with the research question. When we look at the results, we can now directly answer our research question. For the main research question, we ask whether a cloud or local training procedure lower carbon emission. The result shows that cloud training on Kaggle or Colab produced about 21.9% less carbon dioxide overall compared to local training versus code. The main reason is that the cloud GPU complete task much faster, reducing total energy. However, the difference was not statistically significant. So while cloud is generally better. So for RQ1, the model-wise comparison showed two clear patterns. At first, lightweight models like ShuffleNet, MobileNet, and DistilBert were much greener on local desktop, producing 80 to 90% less carbon dioxide. Heavy CNN like VGG19 and DenseNet were far better on cloud, where emission were 60 to 85% lower and training faster. For RQ2, we tested the accuracy of CodeCarbon by comparing it with a SmartPlug reading. The results showed that CodeCarbon estimates were within 20%, which is slightly underestimated CPU heavy models and slightly overestimated or some others. But overall, it was close enough, so we can conclude that CodeCarbon is reliable for student level research. So in the next slide, implication and findings. The findings give us a useful implication. For a student and instructor, the advice is simple. Heavy models should be trained on cloud and lightweight models should be stay on local. Tools like CodeCarbon should be added into the coursework so student can measure and reflect in the environment footprint of their project. This will help raise awareness about sustainability in computing. For policy and research, university can design green computing guidelines that can provide a cloud credits for a large project while encouraging local runs for smaller tasks. And importantly, student research can start reporting not just accuracy but also energy, carbon dioxide, and efficiency scores to promote transparency and responsibility. In finally, limitation and study. Of course, our study had some limitation. We had tested only 12 pre-trained models, so the results may not apply to very large foundation models. Our study was conducted in Bangladesh fossil heavy grid, which means results may differ in countries with more renewable energy. Code carbon with error margin about 20%, especially for CPU heavy runs. Also, our dataset size was small, so statistically significance was limited. We only tested Kaggle and VS Code as a collab platform. Other providers like Avas or Azure might show different results. And finally, our focus was training emission only. We did not include hardware production, data center, and infrastructure. To conclude, our results showed that cloud training emitted about 22% less carbon dioxide than local training overall. But the real insight is about type of model. Lightweight models are greener on local desktop, while heavy CNNs are greener and faster in cloud. We also confirmed that code carbon is reliable within 20% compared to SmartPlug, make it practical tool for students. So our rule is thumb up is clear. Heavy models in cloud and lightweight models in local. By following these rules, students, teachers, and university can reduce emission, finish a project effectively, and promote greener computing practice. And finally, these are the references that we use for our project. Thank you for your patience. That's all.